Thank you for the introduction. Hello everyone, I'm Gong and also from USTC, and today I will present our recent work gSampler, which is a general framework to support faster development of the high-performance graph sampling algorithm for graph learning. So let's begin with the graph sampling. Traditional graph sampling algorithm perform graph transversal to return favorable path or edge list. And most of them adopt vortex-centric programming model, and which offer a set of fine-grained APIs that help define operator or state on each node or edge. Now, to give a quick example, let's look at the vortex ID with node ID 6. The red frontier is including vortex 6 and its first hop neighbors 3 and 5, and it corresponds to the local field of the vortex-centric operator associated with fixed vortex 6. And other than the neighbors, for example, 7, and it's hard for 6 to get information from elsewhere. However, once moving to the graph neural networks, things get significant change. Genes do need sampling also, but the sampling here become a long pipeline with increasingly complex and flexibility. Let me walk through an example. First, the pipeline begins with a getting frontier of the interested set vortices. Let's assume 5 and 6 here. The step may look similar to conversion graph transversal. And then, following that, there may be involving some intensive computation. For example, it's compute sampling probability. It's a real number in the figure. And that step may require information from non-neighboring vortices. Then, the algorithm may perform sampling, but here it's not from a single vortex perspective. Instead, it may perform joint sampling, for instance, and for instance, a layer-wise sampling, and it's to get target subgraph from multiple vortices such as 5 and 6. According to the globe, and it's also due according to the global information, which is computed by us. And finally, as requested by the Zhenkun training usually taking place in the GPU, we have to redrafting the ID space of the produced subgraph. And a more important thing is also with nothing that the Zhenkun training is running in the GPU and often needs to consume sampled subgraph at a large scale. Therefore, sampling speed is also important. Unfortunately, the conventional widely used vortex-centric API and fails to support graph sampling for Zhenkun. There are two general problems. And first is the development effort. We observe that some operators in the complex pipeline cannot easily or completely express use the vortex-centric API. Now, let's walk through the pipeline again. As I mentioned before, vortex-centric API are designed for the graph transversal, so it's working well for the frontier extraction. However, it is not the case for the joint BIOS computation that happen across multiple vortices or edges, as it goes beyond a single vortex scope. The same logic is applied to joint sampling, which is one of the most important steps in the pipeline. And even worse, the fine-grained API cannot express ID reshuffling, which require even more information. For instance, Intel subgraph. To demonstrate this, we conduct a detailed study about 15 Zhenkun sampling implementation, and the high-level observation is that vortex-centric API fail to express many important operators. To address this issue, the current solution is just implement this operator in an ad hoc method. Another important limitation of the vortex-centric API in in context is the performance inefficiency. We have been witnessing that the industry have been adopt GPU for accelerating training. However, there is not enough since there exists a fundamental gap between Forte-centric API and the GPU. In more detail, Forte-centric API failed to exploit massive parallelism of the GPU due to many complex concurrency and concurrency control and the synchronization required by the fine-grained code design, and which GPU cannot perform well. In addition, there is a mismatch between the output format of the Forte-centric API and the requirements of the rest of the other operators. For instance, here, Forte-centric sampling outputs edge list, but the other operator on graph. So to close this gap, developer should add the edge to graph conversion operator by themselves. This introduces overhead and also prevents joint optimization across the pipeline. And to demonstrate the performance problem, we run some sampling algorithms over DGL, and it's a leading joint system that combines Forte-centric API and ad hoc operators for sampling. The results highlight that using CPU for sampling, the entire training process is dominated by sampling. However, even with GPU, the sampling still contributes up to 70% training time. So it's clearly sampling is a bottleneck. All right, recap there. I just iterative that the limitation of the applying Forte-centric API for joint sampling, which looks quite different from the conventional sampling. Basically, we face two problems. First is namely programmable expressiveness, and the second is the implementation efficiency. To address these two issues, we also without involving heavy manual works in the loop, we develop our new framework to make a joint sampling algorithm implementation easy as possible and fast by design. To achieve this goal, our insight is that it's time to not use Forte-centric API, instead moving to matrix. This is because graph can naturally modeled as a matrix, while API associated with the matrix offer more information at a large scope than Forte-centric. The first benefit of this proposal is the programming convenience. Thanks to the greater expressiveness of the matrix-centric API, it naturally supports group scope operators. There, the ID reshuffling can be easily specified as a matrix element remapping. And the matrix API also can express Forte-centric API operator, and consequently, all operator along the pipeline can be unified as a matrix-centric API. So also there's no need to introduce extra format conversion overhead here, because we have aligned the input and output between the operators. And besides programming help, another major benefit is proposing the matrix-centric API is to significantly improve the performance of the joint sampling. This is made possible because GPU are designed to perform matrix computation, and SOSP API offer greater opportunity over greater optimization space. First, matrix computation matches the bulk execution of the GPU and are free to exploit GPU's massive parallelism. And this is done with little or no synchronization overhead. Additionally, this allows us to leverage low-level and high-performance matrix library to get faster execution. And secondly, we can apply many matrix optimization, including computation-wise, such as operator fusion and elimination, and memory-wise optimization, such as select proper format for the sparse matrix. And also, we can explore a joint optimization space for maximizing the performance of pipeline. And to further its programming with the matrix API based on our survey, we generalize the GN sampling process and break into a sequence of the iteration, and each have a 4 step, namely extract, compute, select, and finalize. This ECSF model can cover 15 new GN sampling algorithms that we can find, and designing algorithm within our proposal is simple. One just needs to fill in each source step with the logics written by matrix centric API. Here is an example use the ECS template and our API to implement sampling in paths. We use different color to represent different steps. In each step, our logics are implemented by matrix centric API. For instance, at line 2, we do frontier extraction, and from line 3 to line 9, complex computation is done to get the bias, which involving the tensors. And at line 10, we do neighbor sampling, and the last two lines, we just prepare the frontier for the next loop and return the results to GN framework for training. We not only generalize the modeling, but also the execution and the optimization. To do so, we put all together into our sampling framework gSampler. As it's called, CI is a data flow intermediate representation, and the gSampler takes the user code specified using our API and template as input, and translate into a data flow IR. Following this, we construct many transparent and general code optimization within the IR layer. This optimization can generalize 4 into 3 categories. First is the computation optimization, and for saving resource cycles, for example, including operator fusion. And the second is a storage level within format selection. And the last is inter-batch optimization, and to sample multiple tasks together. And finally, the optimized code are grouped to GN training and shipped to GPU as well. So gSampler is great, and to evaluate the goodness of it, we choose to first show its great experience for improving programming experiments. Here we select 7 most recent algorithms, and they are conventional graph sampling algorithm, whereas the other 4 are sampling for the GN. We compare gSampler to 5 systems that fully or partially use FortiCentrix API. Here are the results. As we explained before, FortiCentrix do well in the conventional graph sampling, but fails in sampling for GN due to the gap between the FortiCentrix API and the complexity of the algorithm. And the DGL prefer an ad hoc method, and lots of effort is missing to develop a graph sampling algorithm for GN. However, in our work gSampler, it is convenient to combine matrix centric API to express diverse sampling algorithms. Next, we shift our attention to performance implementation of the gSampler on both sampling and E2E training. We deploy our experiments with a free 100 GPU with a 16 GB device memory, and we use 4 distances and test 5 baseline. Due to the time limit, I only present the comparative results about GN specific system like DGL or PYG. Across the 4 distances, gSampler outperforms all baseline for sampling. Here we show latest algorithm here. PYG don't support this algorithm due to the gap between the FortiCentrix API and the complexity of this algorithm. And compare to the best performance beside DGL, which is developed by AWS, gSampler introduced 3.88 to 22.3 times sampling speed up. And notice that some baseline which place their sampling on CPU and even run out of time. And the huge sampling speed up have been translated into the training acceleration. For instance, compare DGL with sampling running on GPU. The best performance baseline gSampler introduced 29.9 to 44.3% training time reduction. And note that our sampling optimization doesn't impact training accuracy at all. So to conclude here, I hope in my talk I already convinced you that graph sampling for graph learning becomes increasingly complex and flexible, and leading us to design a new programming model beyond the capability of the conventional sampling framework. And we built gSampler, a general and efficient GPU-based sampling framework for graph learning, with a set of the matrix centers API and a holistic and matrix GPU optimization approach. It has been already open source. And that's all. Thank you for listening.
Go ahead.
Hi.
Hi.
Margot Seltzer from UBC. Thank you for the talk. So I think the graphs that you were evaluating on are mostly sparse graphs.
Yeah.
And the one challenge we face when using the matrix representation is that that's pretty memory inefficient. Yeah. And so I'm guessing, I'm wondering what's the space trade-off that you had to pay for the results that you got?
Okay. For the matrix, it's also sparse matrix in our graph sampling. And we present in CSR, CO, or CSC format. And to get a better performance, we do automatically format selection according to the operator performed in different operator, and joint consider all performance across the pipeline, and to find the best storage format for sparse matrix.
Okay, maybe we can take it offline.
Thank you.
Okay, let me ask a question. I know you're focused on GNN training, but looking at more broader applications of this, I could imagine scenarios where you want your characteristics of your samples to be based on how the samples are being used by different applications. How would you incorporate that type of characterization training into your system?
Sorry, I can't catch you.
If you want samples with different characteristics, is that possible in your approach?
Sorry, and let's talk offline.
Okay. I see another question. Let's move there.
Hi, Xiao from Shanghai Jiaotong University. I think that regarding vertex-centric method, users can actually define complex sampling logic using UDF. So in your system, is it limited that users can only write their sampling method using the APIs you provided and cannot implement several complex logics, for example, branch?
For this question, we currently abstraction matrix API at a very small step operator to do, for example, just okay, and usually UDF in the 40 centuries is composed of some basic operator, yeah, and for example, and node mapper or edge mapper, and we map this operator into the matrix space, So we also provide a similarly operator for this operator, and the user just combine this operator and can get same results as the UDF defined in the vertex centers. And also maybe also for the performance, we introduce IR and general optimization to get the comparable performance. Yeah.
Okay. Thank you very much.
Okay, let's thank the speaker.